on rational functions. In math, when you see the word rational, what should you think? Fractions. A rational expression is an expression that contains a fraction. A rational function is a function that contains a fraction. Okay, which of, this has nothing to do with fractions here, which of these could we classify as a polynomial? We'll just call them A, B, C, and D. A? Do we agree with A? I agree with A. B? Yes. C? No. Why? The variable is under a square root. Under a square root. Ooh, bonus question. How else can I write square root of x using exponents? Campbell? X to the 1/2. Okay, so I could write it not under a radical. I could write it with an exponent, but notice that exponent isn't an integer. Integers are the things that we'd mark a number line with. So fractions, decimals, things like that are not integers. 1/2 is not an integer. This is an integer. This is an integer exponent. Integer exponent, integer exponent, integer exponent, not integer exponent. Okay, what about D? Yes or no? Polynomial or not? No. Why? That's an x to the 1. I can write it 8x to the negative 1. Okay, so that is an integer. So maybe we should clarify a polynomial has only integer exponents that are positive. And then the exponent can be a 0. What is x to the 0? Just 1. Okay, so negative exponents, fractional exponents, things like that are not polynomials. Okay, if we have a rational function, remember I said think fractions, it is a quotient or a fraction of two polynomial functions. So we're going to be dealing with polynomial functions, but they're in a fraction form. Okay, so here's our most basic, vanilla, plain old rational function, 1/x. That's like the most simple rational function we could look at. So y equals 1/x or f of x equals 1/x. Okay, so let's graph it. And we're going to go old school. We're going to come up with some easy ordered pairs. What would you use for x? I know y'all are going to say 1, right? 2, 3, 4, and then I'm going to say, but what about the negatives? And then we'll toss 0 in there. Okay, so here's my fraction, y equals 1/x. So if I put 1 in the place of x, what is 1/1? 1. What is 1/2? 1/3. 1/4? 1/4. Okay, what is 1/-1? -1. -1/2. -1/3. -1/4. 1/0. Ruh-roh. Can we have 1/0? No, that is undefined, right? So I'm going to nix that. Undefined. Okay, so how am I going to graph something if it's undefined? I may have to use an open circle. Okay, we'll see. Yes?
I think we should also include -1/2 and 1/2 on the x.
Oh, I think you're right. I think that's what we were about to do here. Thank you, Max. Let's try some fractions. And the reason is, before I do that, let's see why. Let's plot these. Okay? 1, 1. 2, 1/2. 3 1/3. It's getting kind of hard to accurately graph that, isn't it? Okay, then I have -1, -1. -2, -1/2. -3, -1/3. Okay, what is that graph? It's not very telling, is it? Like, it doesn't look like anything I've ever graphed. Not really, but it doesn't look like anything readily recognizable, right? So that's how some fractions here are going to come in handy. So I'm going to do 1/2, 1/3, 1/4, -1/2, -1/3, -1/4. What is 1/1/2? 1 times 2/1. Keep, change, flip. 2. What's 1/1/3? 3. What's 1/1/4? Come on, y'all know the answer? 4. What if I just make it negative? Awesome. Now, let's plot those. Okay, 1/2, 2. 1/3, 3. These also get a little bit hard to graph, but it definitely gives us a clearer picture of what's going on here. And then do the negatives. What does that look like? Kind of looks like two parabolas, doesn't it? That are turned sideways. Like, doesn't that kind of look like a parabola? Doesn't that kind of look like a parabola, but they're like wonky? Okay, so we already said that we can't use x equals 0. Is there anything that I could put here and get 0 for y? Can I figure out 0 equals 1 divided by something? No, because there's nothing that I can multiply by 0 to get 1. Right, so this is not possible either. All right, so I have a situation where I can't use x equals 0, and it's not possible to get a y of 0. Okay, so what that means is I've got these restricted values. One of them is an x and one of them is a y that aren't going to be used. So what that ends up creating is an asymptote. And I'm going to dot this asymptote, and then I'll write that word out because that's a strange little word. All right, so this dotted line is like a break in the graph. And we just dot it to show where it is. It's not part of the curve, but it's showing the boundary of the curve. Yes?
Are we going to do limits as exponents?
You got it. Okay, and there's that forbidden or not possible y value of 0 also. So can you see once I draw those little pink lines, and this is how you write the word, asymptote. This one is vertical. And if I wrote the equation of that vertical dotted line, what would the equation be? X, the dotted line is x equals 0. You're right, x can't be 0, but that line is x equals 0. Okay, over here, this one is a horizontal asymptote. And that line's equation is y equals 0. So those are the two values that we couldn't have. Those are the two not possible undefined values on this graph. So those create a break in the graph and kind of like a boundary for the graph. Okay, now we plotted those little points, but now let's actually connect them because we still don't have the curve represented. So I'm going to connect these. And they are going to, all those points are going to stay inside those asymptotes. And the same down here. So I have these two curves bound by these asymptotes, or undefined or not possible values. And all together, this graph is called, does anybody remember? It starts with an H. Hyperbola. Okay, so the curve itself is called a hyperbola. The curve has two asymptotes, one vertical, one horizontal. It's kind of a complex graph, isn't it? Like it's more than just a U or a line. There's kind of a lot of pieces and parts to it. Any questions on why that graph looks the way it does? Okay, so let's look at this next question. What happens to the y values as the x's get very large? So if I kept making a table and I used x equals 10, 1,000, 10,000, what would happen to these y values? They would get incredibly small and really close to what number? Okay, so the y values get very small and closer to 0. Okay, what happens to the y values as the x values get very small? And what I mean by that is like negative 10, negative 100, negative 1,000. What's going to happen to these y values? Are these going to get bigger or smaller? Technically bigger, right? Is negative 1/2 or negative 1/4 bigger? That kind of messes with your head. Technically it's bigger, but they are also going to get closer to what number? 0, just from the negative side, right? So if we think of it as kind of like a limit, picture a number line. Hang on, let me write this down and then I'll show you what I mean by number line. Also, y values will get closer to 0, but from the negative side. There we go. Okay, so if I were to think about a number line here, okay, so if I thought of this in terms of like a number line, and here's 0, then these y values over here, the positive ones, we're actually inching in closer to 0 from the positive side, or from the right side. And then these numbers here are actually getting closer to 0 as well, but we're coming in this way. What does that make you think of that we've talked about recently? Limits. From the left, from the right, we're approaching 0. That is a perfect limit situation. Okay, so what happens to the y values as the x values get close to 0 from the positive side? Okay, so what I'm talking about here is, look at these x values. Isn't 1/2, 1/3, 1/4, isn't each one closer to 0 than the previous one? Okay, but what happened to the y's? They got larger. Okay, what happened over here? They got smaller. The opposite effect. Okay, so from the positive side, y values get larger. I'm going to say towards infinity, because isn't it going to just keep getting larger? If I used a 10 for an x, then 1/10, then it would be 10. 1/100th would be 100. So it's just going to always continue getting larger. From the negative side, they're getting smaller towards negative infinity. Okay, so that's a whole lot of words. You know, we don't like to write a whole lot in math. We'd much prefer to use symbols. So I can write all the stuff that we just wrote out much easier if I use limits and some symbols. Okay, so let's do this. What happens to this function, f of x, as x approaches 0 from the left? Okay, and more so than the table of values, I would just look at my graph. Okay, so I'm going to approach, x is going to approach 0 from the left. So let's go back up to the graph. Here's where x is 0. This is to the left. So if I'm coming in from the left, and these x's are getting closer to 0, what's happening to the y's? They're going down, 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 down forever and ever. So they would approach negative infinity. Limit as x approaches 0 from the left. So I'm coming in this way on my graph, and those y values just continue to drop lower and lower. Okay, what about the limit as x approaches 0 from the right? So now I'm going to talk about the limit as x approaches 0 from the right on this graph. I'm looking at what is happening to y. Okay, so let me slide back up to my graph. I'll let y'all write that out. Okay, approaching 0 from the right. Now I'm coming in this way on the graph. These values, the x's are getting closer to 0, but the y's are just getting bigger and bigger and bigger. So the y's are approaching what? Positive infinity. Okay. So what is the limit as x approaches 0? Does not exist. Well, how can I say that? Because I had a limit from the left and a limit from the right, but they didn't agree. So if they are in disagreement, then the limit just approaching 0 in general doesn't exist. Yes, ma'am? Uh-huh. And if they were both positive infinity or both negative infinity, that's cool. That would also be the limit here. Okay. Any other questions? All right. Actually, I'm not done. All right, I'm going to do 2 more over here. I'm going to squeeze them in. I want to think about the limit. We haven't done this one yet. Not a trick question, just trying to stretch our brain a little bit. What am I asking you? The limit as x approaches infinity. So I'm saying as x gets bigger and bigger and bigger and bigger, what is happening to y? Okay, so let's go back up to the graph. Wait till most of the pencils stop moving. All right, go back up to the graph. X approaches infinity. Okay, here's my origin. Out here, x's get bigger. So I'm saying, all right, what's going to happen to y as x is 10, 100, 1,000, 10,000? What's happening to the y values? They're getting smaller and closer to 0. So I have a limit of 0 there. As x's get bigger, y's get closer to 0. Will they ever get to 0? No, we already said we can't have a y of 0, but that doesn't matter. Remember, limits are about what you are approaching. Okay, one more. Squeeze in. What about the limit as x approaches negative infinity? So it's saying, okay, let x be negative 10, negative 20, negative 30, negative 100, negative 1,000. On my graph, that's out this way. So as x's are moving out this way, what's happening to the y coordinates? They're getting closer to 0 also. From a negative side, like these are all negative y values, but nonetheless, I mean, they were inching closer and closer to 0 pretty quickly just in these few points right here. So this limit would also be 0. Question? Okay, please stop and ask if you have a question. Oh, my tools keep falling. I could use this to like pinch somebody who's on their phone when they should be paying attention. I could like pull a hair out right there and you wouldn't even know it because you'd be so absorbed in your phone. Okay. So the lines that the graph is approaching are called asymptotes. There it is written again. Rational functions often have horizontal asymptotes, vertical asymptotes, slant asymptotes, or a combination of these. Okay, so for today, we're going to talk about the vertical and the horizontal. All right, vertical asymptote. Definition. So we already looked at one on a graph. We analyzed it, but let's look at the official definition. Vertical asymptote. The line x equals a is a vertical asymptote for a function f of x if, oh dear, f of x approaches positive infinity or f of x approaches negative infinity. Remember, that's another name for y. So if y is approaching positive or negative infinity as x approaches a number from the left, right, or both. Kind of complex, isn't it? So looking at the graph that we just made, there's a vertical asymptote at 0. All right, so let's pick this apart and see how it applies to that graph. Does y approach positive or negative infinity as x approaches, remember our vertical asymptote was 0. So as x approached 0, did f of x approach positive infinity or negative infinity? Let's see if that's true. As x approached 0, did y approach positive or negative infinity? You'll write that down, then I'll flip back to the graph. Okay, going back to the graph. As x approached 0, did y approach positive or negative infinity? Okay, here we go. As x approached 0, all right, x is approaching 0 from the left. Graph is going down to negative infinity. We're approaching x equals 0 from the right. The graph is going up to positive infinity. That, according to the official definition of a vertical asymptote, tells me that 0 is a vertical asymptote. Because as I'm approaching 0, it's doing this. I think I did it backwards for y'all. Yes. It's doing this. As I approach 0. All right. Official definition of a horizontal asymptote. The line y equals b is a horizontal asymptote for a function if y approaches b as x approaches infinity or x approaches negative infinity. Okay, remember my horizontal asymptote on that graph was 0. So is y approaching 0 as x goes to infinity or negative infinity? Well, let's look. Does y approach 0 as x goes to positive or negative infinity? X goes to positive infinity out here. Yes, the y's are getting close to 0. Out here, as x approaches negative infinity, the y's are approaching 0. Therefore, 0 is a horizontal asymptote. Okay? Now, generally speaking, you can look at a graph and see a vertical or horizontal asymptote. Like, it will level out, and it will do this, or this, or this at a vertical asymptote. They're kind of easy to spot graphically. All right. So yes, we denote asymptotes on a graph using dotted lines like we already did. Okay, we are going to get some graphing calculators out. If you have your own, please get that out. If you need to borrow one, maybe send someone from each table to come over. Since it's like an obstacle course.
Can you make sure that you specify that graphs can have more than one variable?
Yep.
Because
And a hole.
Because what is it, cotangent that has
Infinite.
has infinitely.
So does tangent. Well, so does secant, cosecant. Yeah. Those 40.
All
Yes. Threw some in here that have 2.
We're gonna learn about cusp.
Cusps. Pardon me. Oh, wait. Okay, I have some more. Y'all. I'll get them over here. Raise your hand. How many more do I need? Just 2? Okay. 3? A lot. Just 3 a lot. Is that it? Okay. Alright, does everybody have one now? Turn it on. Is it working? Sometimes over the summer we get some dead batteries. No, because I might get 2 more years out of some of them.
Well, if it grows,
Yeah, but if they corrode, I can clean them like with alcohol and a Q-tip, and we're good to go. Batteries are expensive.
I'd say take them out, put them in a box.
Okay. How about I get a calculator? Y'all, I almost cried the other day. Like, literally almost shed tears. I had my own calculator and it had like a baby blue plate on it. And I've probably had it, no lie, close to 20 years. Like, I've used that calculator longer than y'all have been alive. And it just totally died this week. Tried multiple new batteries. It was the calculator. And it made me very sad. So, using this one. I kind of liked my old school one. But anyway, here we go. All right. So, we're going to graph the following equations on a graphing calculator to determine the translation of the parent function. What does that mean? We're going to take this parent function back here, that plain old vanilla graph, and we're going to slide it or flip it or do things like that, right? Move it around, change it somewhat. Okay, so we're going to look at it, we're going to describe the translation and figure out where the vertical and horizontal asymptotes are, and then just do a rough sketch of it. Okay, here we go. Has everyone graphed on a graphing calculator? Some no's? Okay. All right. Good. We'll go slow at first here. Go to the top left button, y equals. If there is anything there, hit clear. Clear them all out. All righty. You have a fraction key on a graphing calculator, but it's hidden. I don't know why they don't put a button on here, but they don't. Okay, to get a fraction key, we're going to push alpha, y equals. And you should have this little menu that pops up. Okay, and we want that first thing, numerator over denominator. Alpha, y equals. If someone around you needs help, help them out. Alpha, y equals, we'll get a fraction.
Say like 1 divided by.
Yes. Okay. Shh. Listen, guys, that was a good question. Hey, shh. Can you just do 1 divided by? Yes, but the entire denominator must be in a set of parentheses. If it's not, you will get a graph, but it will be wrong. Or it won't be what you intended. Okay, so I have 1 over x plus 5. X is right next to your alpha key. Okay? Wave your hand if you need help. Okay, now we're going to push the magic button, and we might need to change some things on some calculators, but hopefully most of us will get this graph. What numbers? On your y equals? That one. It's A on your paper here, if that's easier to see. 1 over x plus 5. Okay, if your graph does not look like this, I want you to try this first. Push zoom, right here, zoom, standard, 6, so zoom 6. And that will always, it's like goes back to a home graph of 10 to negative 10. Okay, now if your graph does not look like that, raise your hand. Okay.
I'm pretty good. I'm not even gonna go home and be like, oh, don't even like fucking go pre-calc right now.
Alright, hey guys, if you took AP Stats, if you are not getting a correct graph, go to your stat plot. You probably have one on. Check that.
Put it on my gate.
Alright, who else needs help? We're all on the same page. Everybody has this lovely graph.
Absolutely.
All right. Woo. Can you visually see a vertical asymptote there?
Yes.
Where is it? Okay. What if it was not something easy to count? What if it's something not easy to count? How can I look at the equation and know that it's going to be at negative 5?
Whatever gives me the opposite of what x is in the equation.
Okay, so what would make the denominator 0? That's where that asymptote is. Okay, so if I look at that denominator, that's pretty easy to mentally go, okay, x can't be negative 5 there, so I should expect a break in the graph at negative 5. Yes? You're good? Okay. Okay, can you see visually a horizontal asymptote? And what I mean by that is, if you look out to the edges of the graph on the right or the left, is it leveling out? Clearly. What is it leveling out to? A y value of 0. It would make the denominator 0, and that makes the function undefined. Okay, any other questions? Okay, so let's talk about how we would sketch this. So we're going to do, let's go back and answer the question. What's the translation of the parent graph? The one that we graphed on the first page, how would you describe this? Shifts 5 to the left. It is still a hyperbola. You're exactly right. Okay, so this was a shift left 5. Does left 5 seem a little odd because that's a plus 5? Remember with the absolute value and the parabolas, the same thing happens. If I have a plus 5, it's going to go left 5 because negative 5 is the undefined value. If it's a minus 5, it's going to go right 5 because positive 5 is now the undefined value. Okay? All right, so let's talk about, let's use an abbreviation because I don't want to write asymptote every time. Let's do horizontal asymptote at y equals 0. That's that horizontal line that it was approaching out to the edges of the graph. vertical asymptote at x equals -5. That's where the vertical line that kind of chops up the graph into two pieces would be found. Okay, so let's see how we would sketch this. So we're not going to do a whole lot of exact points like we did previously. I know what the general curve looks like, and I know where the break is. So let's clearly write where the break is. 1, 2, 3, 4, 5. I'm going to make my dotted asymptote. And then y equals 0 is where that horizontal asymptote is, so I'm going to dot that. And that kind of divides up my graph into the different regions that I need. And then we're just going to fill in the curve. Now, one thing I don't like about these calculators, it makes it look like the graph stops. Does it? No. So don't tell me on your paper that it stops, because we know that it doesn't. So for my graph, I'm going to fill in this curve and that curve, keeping it within the boundaries of the asymptotes. Okay? So the real exact values that I'm really worried about are where the asymptotes are, and as far as the curve goes, we just sort of sketch it in. Any questions on any of that? Okay. All right, let's go to this one. -2/x. What do you think the negative will do to my parent function? Flip it how? Over the x-axis. We'll flip it over the x-axis. What do you think a 2 will do to it? Stretch it vertically, but I'm going to be honest, we probably won't notice that difference. Okay, so the 2 will just be a stretch that won't be very noticeable, but the negative will definitely be noticeable. Okay, so let's go to y equals. Let's type in this function. Alpha y equals gets that fraction. Got it ready? You're ahead of me. And push the magic graph key. So maybe you can kind of tell that it's been stretched a little away from the origin. That's where the 2 comes in. Like I said, not very noticeable. Did it shift left or right? No. But it did flip over the x-axis, didn't it? Remember, our parent function was here, and here in quadrants 1 and 3. Now it's in quadrants 2 and 4 because it reflected over the x-axis. Okay? All right, so let's describe the translation. How would I say, put that in words? Reflects over x-axis. 2 is a vertical stretch, but it's not that noticeable. I'm going to put a 2 there. 2 is what does that. And horizontal asymptote is where? Yeah, still y equals 0. You can visually see that on the right end of the graph and the left end of the graph, that's kind of leveling out at 0. Vertical asymptote is where? X equals 0. And don't tell me just 0, because is it a vertical line at 0 or a horizontal line at 0? So we have to name the entire line there. Okay, so let's sketch. Get some dotted lines in there for our boundaries. And these are technically on the axis. I'm just doing them right next to them so they show up. And then my graph fills in this quadrant and that quadrant. It's still called a hyperbola. Questions? Can you wait just a little bit? Or do you need to go now? All right, next one. I want you guys to work on these two for me. You may look at the graph, look at the equation, and talk about the shift and the asymptotes. And I will walk around and answer questions.
Well, no, you're not doing English transfer. I said BC on this class.
Ask if you have a question. Calculator or just
What?
graphing in general question.
Draw the graph. Needs help. Alright, what's going on with that one? Okay, how much in both? And I'd say look at your equations very high. Perfect. And what about that negative in the front? Remember your parent function is in these two parts. And now it's kind of elected, yes. What is it? It was what Anybody have a question? Yes.
One answer.
I'm typing that exact thing.
Shifting shores.
I'm gonna work an hour early to get away from money. Well, then before yeah, I literally left. I was working super straight. I left 6 o'clock. Went there, got a call from my thing just after 5. So I went to Hilltop and back. Pulling into Hilltop. Russell pulls in right behind me. As he's
Metal or plastic? All right, are we ready to talk about them? Someone is on their phone and I haven't graphed it. Tyler Clark.
Sorry, I forgot to grab it.
Okay, I'm going to start on this one. All right, what is our translation for this one? Right 3. Shifts right 3. Okay, so our graph needs an asymptote that shifts right 3. So everything will shift right 3, including the asymptote. Now, what about the horizontal asymptote? If I take this horizontal line and I shift it right 3, it's still along the x-axis. Okay, so what are those asymptotes? Horizontal asymptote at y equals 0. Vertical asymptote at x equals 3. Okay, so we got the shift, we have the asymptotes identified, and now we will just sketch the curve. It's still kind of in that first and third quadrant. We just have to stay within these asymptotes. Question? That one was pretty simple. Oh, and there is a vertical stretch. I guess I should put that. Even though, I mean, you really can't see it, can you? Vertical stretch. Huh? Yeah, it's like by a factor of 4. Yeah. I mean, it's easy. If you stretch a line, that's easy to see because it changes the slope. If you stretch an absolute value graph. That's easy to see. These are just not so easy to see. Okay, so let's talk about this one. This one was busy. It had a lot of stuff going on. First of all, what about the negative out front? What does that do? Reflects it over what? X-axis. So reflects over X-axis. Tell me about this plus 2. Shifts left 2. And you should be able to visibly see that on the graph. But even without graphing it, I know it's going to shift left 2 because of this plus 2 inside that fraction. But what about the minus 3 after the fraction? Down 3. And it does have a vertical stretch. I'll put that up there. Okay, so let's graph it and then we'll name the horizontal and vertical asymptotes. Okay, so when I shift left 2, that vertical asymptote is going left 2. So you should be able to visibly see that imaginary line that's there. And then down 3, the horizontal asymptote, if we shift everything down 3, it goes down as well. Okay, so those are my 2 asymptotes on the graph. I'm going to go ahead and name them up here. Horizontal asymptote at what? What's that line? Y equals negative 3. And then there is a vertical asymptote at x equals negative 2. And normally my curve would still be within like these 2 quadrants, but remember we flipped it. So now it's actually here and here. Kind of ran out of room there. Kind of fun to graph. Oh, all right. Let's talk about this graph. Graph it on your calculator. X minus 1 over x minus 2. Shifted, right? This one has a variable up top, so this one's a little bit different than the ones we've graphed so far. Can you tell me about the horizontal shift? Right 2. How do we know that? Yep. What would make that denominator undefined? X equals 2. So x equals 2 is the vertical asymptote. And you can see that. What about that horizontal asymptote? Is it 0? Yeah, it's a little shifted, isn't it? And look, I mean, this is crossing over 0 and then leveling out. This is coming down and it's not quite reaching 0. So it's definitely changed. Okay, so how do I know, like, there's not a plus 1 after here? How do I know what that horizontal asymptote is? Okay, I'm going to show you a new little trick on your table. Okay, so go to second graph, which will be your table. Okay, so this is where you can get some ordered pairs on your graph. If you needed some exact ordered pairs, then this is where you would go and get those points. And you could scroll up and down and see the Y values there. Okay, I'm going to change my table a little bit. So let's go second window. Do you see where it says table set? I'm going to go second table set. Okay, to remember what the definition of a horizontal asymptote is, like you want to look out there as x approaches negative infinity or as x approaches positive infinity, what is y approaching? So I don't want to, I'm not interested in x is negative 7. I want to know what's happening maybe at x equals 100. So I'm going to start my table at 100. And then delta in math and science means change. So I don't have to go by ones in the table. I could go by 10s or 20s or 30s or hundreds or whatever. I'm going to go by 20s. Now, let's go back to the table. So second graph will get us back to that table. Are yours in fractions or decimals? Okay. I don't know how it decides what it wants to do with these. Look at those fractions. What are they really close to? 1, right? Look, 159 over 158, like that's practically 1. 119 over 118, that's practically 1. So that tells me that that's what those y values are approaching, y equals 1. That verifies that on my graph, the horizontal asymptote is 1. Yes, ma'am? Technically, it won't ever reach 1. Sometimes, though, on the table, if you do large enough numbers, it will eventually go, okay, it's 1. Just because, yeah, it only has the capability to round or, extend those decimals so much. So, eventually, it will concede that it's 1, even though technically it's not. Kind of like the football was never technically crossing the goal line. Okay, so let's talk about how we graph this. Let's mark the asymptotes first. So we had a vertical asymptote. Okay, guys, we're almost done. Stick with me. Vertical asymptote at x equals 2. So go to 2, dot the line. Okay, horizontal asymptote was at y equals 1. Dot the line. And then we could just fill it in. Stay within the boundaries of the asymptotes. So you're getting closer and closer to those asymptotes without crossing over them. All right, let's finish out this page. We'll finish out through example 4, and then we'll break there and we'll finish the notes tomorrow. Okay, so due to undefined values, most rational functions have restrictions on their domain. To determine the domain of a rational function, set the blank equal to 0 and solve. We've talked about that already. Denominator. Yes, I'm interested in what would make this denominator 0. And that is where our undefined values are found. The solutions, if any, to this equation being set equal to 0 will be the restrictions on the domain of the function. These restricted values create breaks or discontinuities in a function's graph. Okay, so for example, just look at this last one here. What made the denominator 0 was 2. That's where that vertical asymptote occurred. That created a break in the graph. Okay? All right, so we're not going to graph them. We're just going to look at these and determine what x can't be. And then we're going to state where the vertical asymptotes would be. Okay, so what can x not be here? 0. 0 is the only number that would make that denominator 0, so I can't use 0. Okay, so this is the way I would state my domain. There are two ways. I can say x can't be 0. There would be a vertical asymptote at x equals 0. Okay, there's another way I can say x can't be 0, and this is using interval notation. With interval notation, we do the smallest, comma, largest value. So if it can't be 0, picture this on a number line. It could be anything but 0. Okay, so I'm going to say it could be from negative infinity to 0, union 0 to infinity. Do you remember those from Algebra 2? Okay, so that means I can have the smallest number imaginable go up to 0. The parentheses means same thing as an open circle. It means don't include it. Then union means in addition to. Pick up just to the right of 0 and go as big as you want here. Now that's easier, isn't it? X can't be 0, but they mean the same thing. Yes. Union means together with. So it could be from negative infinity to up to 0, but not including it. Also from 0 to infinity. Okay. So notice technically I've skipped 0 because I used parentheses. If you want to include something, use a square bracket. Okay, so, oh dear. Let's look at this one. How do I figure out what would make the denominator 0? Set it equal to 0. 2x squared plus 5x minus 12 equals 0. Should we just try some numbers randomly and figure it out? Factor it. All right. Figure out your factors. How many of you like this method? Y'all look like a deer in headlights. Y'all like, what? How many of you do guess and check? Oh, lordy. Okay. All right. Let's talk about different ways to factor this. 2x squared plus 5x minus 12. So I'm trying to figure out what two factors make this the product. Okay, here is guess and check. That first term is 2x squared. What two things do I multiply together to get 2x squared? X and 2x. 2x goes in one of them, x goes in the other. I'm going to go to this last number, negative 12. If it's a negative 12, one of these is going to have to be positive and one will have to be negative. Now, I have options. It could be 12 and 1. It could be 3 and 4. It could be 6 and 2. Sorry, y'all can't see that. I have to figure out the right combination so that when I FOIL this out, that outer and inner product will give me positive 5. Okay, so whatever number I put here and here, this product combined with that product has to give me positive 5. Anybody see what it needs to be? 3 and 4. Because this product is 3, this product is 8. How do I get positive 5 out of that if that's negative and that's positive? So that's plus, that's minus. That's guess and check. If it doesn't work, then you go back and you either try flipping these or picking a different combination. Yes. Yes, that's the X. With Coach Harper. Coach on have. Oh, okay. So did you? Let me show. I think it's linked to this. Let me show you. That's why y'all were looking at me so weird. Okay, so if I talk about 2x squared, come on, y'all, hang with me here. This is A, B, C, right? In terms of like the quadratic formula. Okay, A, B, C. Okay, I need to put A times C at the top. 2 times negative 12 is negative 24. I need to put B at the bottom, which is 5. And then you are finding the combination of any numbers that will multiply and give you that, but add up to give you that. 8 and negative 3. Doesn't matter which side I put it on. Okay? Now, I am going to, there are two ways I can go from here. Okay, let me show you one way. I'm going to bring 2x squared down. I'm going to bring this plus 8x and my minus 3x. That's coming from here and here. Some of y'all are not paying a bit of attention. I think you probably need to. This is replacing the 5x. I'm bringing the 12 down. So I took that combination that gave me AC up here and B here and putting those terms here. Now I can use factor by grouping. I think Coach Harper uses this method if you had him for Algebra 2. What do these two terms have in common? 2x. Times what? X plus 4. What do these two terms have in common? Negative 3 times x plus 4. Okay, this should be the same. And that is one of your factors. And the other factor is this combined with that. So I have 2x minus 3 and x plus 4. Those are my factors. Okay, another way, bottoms up. Does anybody use bottoms up? Okay, I still start this way, but this is what I do next. I make this x plus 8 and x minus 3. And if I have a coefficient that is not 1, this coefficient, lead coefficient is 2, then I have to put both of these over 2. If it reduces, we reduce it. That becomes x plus 4. If it doesn't reduce, then that number comes up in front. Got the same thing. Okay, is that the way y'all did it? Okay, there's 3 options.
Where y'all learning these things?
You figure out which one works for you and just do that one method. Yes. Did y'all make a box? Shh. So you get this. Yes, so it's kind of a version of this. Okay, so what, you don't have to know all the methods. You need to know one method that your brain likes. Okay, and factoring will never, ever, ever leave math. Like, it's not something that we're just reviewing today. Max, you factor forever, don't you?
To a certain extent, yes.
For certain problems, you're always going to need to know how to factor.
Especially once you hit big, large things, you're gonna want to know how to take out big numbers so you can get.
You gotta know it. Okay, so let's. Oh, come on. 2x minus 3 and x plus 4. Didn't Miss Clark give your class factoring practice like day 1 or 2? Did y'all do them?
Yes.
Okay. All right, let's start with this one. Shh. What makes this 0? What makes this 0? Close. 3 over 2. Okay, so if you're not sure, you're going to just set that equal to 0. Set that equal to 0, and we get those two solutions. So what is my domain? X cannot be these two numbers because those are the only two numbers that make this fraction undefined. Create a 0 in the denominator. So my domain is x cannot be 3/2, comma, -4. And I don't have room for interval notation, so I'm going to leave it at that. Okay, last one. What makes this denominator 0? Okay, plug it in and see if it works.
I will say, sometimes factoring is not the thing you should do. You remember that huge problem I had on your board one time? I factored and simplified, and then I got it half wrong. She's like, why did you do that?
That was the teacher.
That was his boss. I'm like, it's still right.
All right, what makes this 0, guys? I keep hearing -2, but what do I get when I square -2? What's 4 plus 4? Not 0. 2. Okay, what's 2 squared?
It's 2i.
What's 2 squared? What's 4 plus 4? Okay, what makes this 0? Nothing. Nothing will make it 0. Okay, so look, if I do this, what number can I square and get -4? Okay, an imaginary number. We're not dealing with imaginary numbers.
Yes.
So there's nothing, no real number that I can square and get a negative anything. So what is my domain? What's the restriction? Yeah, no restriction. Domain is all real numbers. Nothing makes it 0 in the bottom. Alright, we are going to stop there. Hang on 1 second. Hey guys, hang on 1 sec here. I want you to play around on this Delta Math tonight. And I will know who does it and who does.